Swayam Prabha. Digital India. Educated India.
But right now, what I want to essentially say is, so we are going to look at models of this form, right? So which are called as linear models, where your prediction function h, the one that you're trying to learn, is just a linear function of your input variables, right? So you have x, a vector x, which has d numbers, and then basically by linear I mean you are giving weights to each of these features that you have, right? So you want to say when I'm going to predict the price of the house, I'm going to weigh the location 100 times, the population in the location maybe 50 times, and so on. So these are your numbers W1s to these are your weights, right? Right. So that the way that we are weighing each of these features. So we are going to say now that our prediction is a linear combination of our weight vectors. That's what we are saying, right? So the way we will represent that is using this notation W transpose X, where W is a vector of weights and X is your feature vector, right? So I can, before going further, so let's look at a small example. Just to see if you understand this notion better. So what is the equation of this line? So let me call this x1, this is x2. What's the equation of this line? Sorry? Yeah, x2, x1 minus x1, x1 plus x2 equals 0, right? So that is the equation of this line. So this is one way to look at this. The other, however, the way that we'll look at, which is easier when you go to higher dimensional, is it's a simpler way to look at this, which is I'm just going to say this is 1 into x1 plus 1 into x2 is 0 for whatever reasons, right? And the way that I will rewrite that is this as a dot product of two vectors, right? So now this is typically the type of vectors which we will call as W, and this is typically the vector that we will call as X, right? And this equation is W transpose X is 0, where W is our 1, 1, and our X is x1, x2, right? So if this is the case, how does the vector W look like, right? So where does the vector W point to? The vector W is pointing in this direction, right? So this is our W, which is 1, 1, and this is our x1 plus x2 is 0. So if I had to ask for the equation of W transpose X equals 2, how would that be? So the W stays in the same direction. So W transpose X equal to 0 is the set of all points which are perpendicular to the vector W, which is 1, 1. W transpose X equal to 2 would be just pushing this in this direction, right, by distance of 2, right? And if it is minus 2, it is going to push it in the other direction, right? So this is one thing that we would need later on. The other thing we might need later on is, so if a function f of x is W transpose X, right? So what can you say about the vector of partial derivatives of this function with respect to coordinates of W, right? What is this? So basically what I'm asking is, this is dou f by dou W1, dou f by dou W2, and so on, dou f by dou W d. What is this vector? Sorry? So what is W transpose X? By our definition, it's just W1 x1 plus dot 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 WD xd, right? So if this is the case, what is the derivative of W1 x1 plus till dot 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 WD xd with respect to W1? With respect to W1. Sorry? So basically you set everything else constant and then you just differentiate with respect to W1, right? And what is that? So that is just X1 in this case, right? So this is just X1, this is just X2, this is just XD, right? It's just X, basically, the vector X itself, right? So this is what we call as the gradient, which is just a d-dimensional generalization of our usual derivatives, right? So we will see why this is important as we go along next, right? Okay. So let's go forward. So this is the goal now. So right, so we have fixed what our set of models is, right? So our set of models in this case is a linear model, which is just a linear combination of our feature vectors, which is W transpose X. And we want to minimize W, function f of W, right? So it's a function of W because we want to learn the best W for the data that we have, best linear W for the data that we have, which means the objective function that we have is this, basically. This is our objective function, which is just our prediction minus the actual label, right? Prediction minus actual label squared, which we agreed upon as a reasonable function to start with, performance measure to start with, and then this is our objective function that we want to minimize, right? So how do we go about minimizing a function, right? Why is there a half? So we can do it without half. So a question for you. So let's say some W minimizes this function without the half, right? So if I add the half, what would happen to the W that minimizes the function? Would it change or would it not change? Would it change or would it not change? It would not change, right? So because the argument, I mean the W, this scaling this function by any number is not going to change the actual W that is the answer to this problem. The reason why we put half is just for mathematical convenience, so that terms cancel each other. So otherwise nothing else, right? So you can do it even without the half, and things will still work out. Okay, so how do you minimize a function? So what have you learned the way to minimize a function? Given a function, how do you find the point that minimizes the function? What condition should that point satisfy? Differentiate it, and what happens? Set it to 0. I hope you know why that is all done and so on, right? So that's basic calculus. So I'm not going to do much into that, dwell into that. So in this particular case, if you differentiate this function with respect to the W, the parameter of interest, it's going to come out like this. So let's quickly see why that is the case. Right, so if I differentiate this function with respect to W, so what happens? So this is just half into sum of, so dm, I can think of this as W transpose xi squared plus yi squared minus 2 W transpose xi yi, right? So this is what it is. Now I am differentiating with respect to W, so I know that this term is half sum of I equal to 1 to m 2 W transpose xi into xi. Yi does not matter in the differentiation because you are not differentiating with respect to W. W does not occur. So what happens to this? So this becomes minus 2 xi yi, right? So is this clear? So the way I have differentiated this with respect to W, right? So this is 2 times W transpose xi times the differentiation of W transpose xi, and we just saw that if you take the gradient with respect to W of W transpose x, it's x, right? So and hence we have xi here. So now you should be able to see why I put the half there, because this 2 comes out common and then it cancels, and this is what we end up as the gradient, right? And now you set the gradient to 0, and whatever you get is this. Now this is this. Okay, so first of all, what happens is this is what is called as the. Any idea what this is called as? What this thing is called as? So basically, this function is what we set to 0, right? So if you set this to 0, so you take this to the other side, so this becomes equal to this, right? So now it's W transpose. What is this? Is this a vector, or what object is this? Sorry, you said something. So what object is this? A number, vector, or a matrix? How many of you say number? Okay, some of you say number. So so if it had been xi transpose xi, right? So that would be a number. If it's xi transpose, that's actually a matrix, right? So this is a matrix. So this is a sum of matrices, which is again a matrix. So this matrix times a vector is another vector. So that is the equation that we are trying to solve, right? So you can think of it W transpose some matrix A equals some matrix B, right? So where this this is a vector B, right? So this is the equation that we get, where A is this matrix and B is this vector, which means our W can be written as, you take A to the other side, right? So it becomes A, typically A inverse B, whereas when you're dealing with matrix and inverses, you should be very careful. The matrix may not have an inverse, right? So what we call as something called as a pseudo inverse, which is like an inverse, but not really. So I'm not going to go into the details of what a pseudo inverse is, but eventually what we end up is we get a closed form solution for W, right? So that's more important. Closed form solution for W for linear regression. Basically, to recap, so you were given this data set, you fixed your model to be a linear model, and then you try to work out what is the best W that fits this. And it so happens that the W, of course, what should it depend on? It should depend on only your data, and the way it exactly depends on data is given in this form. So now, of course, we want to understand what this unwieldy looking expression means, right? So we cannot just say that, okay, so this is the W that answers our question, but we want to understand what this W is a little bit more. That's what we'll try to do next. Let's try to look at a geometric view of linear regression, right? So let's look at this matrix X, right, whose columns are our x1 through xm, right? So each of this is a vector that vector of features that were given to us. So what dimension is this matrix now in? So what is a column? A column is one particular feature, which is in what dimension? So so this is each day's observation. Think of this as m days you have observed the data. You have observed pressure, air pressure, humidity, and so on, right? So x1, this is just number 1, 3, 5, 8, let's say, right? So these are our features, right? So what dimension? We agreed that our features are going to be in D dimension, right? So each of this column is a D dimensional vector, and we have m of them. So what matrix is this? What is the dimension of this matrix? It's a D cross M matrix, right? So that is what this matrix is. And let's call the rows as V1 through Vd, right? So I'm just going to give some names to these. I'm just calling V1 through Vd. So what is Vi? What dimension is Vi? 1 cross M. So what is it doing? So it is taking the first feature of every data point, right? So if it was like, let's say, the temperature of 100 different days, it's just computing, it's just looking at the temperature of all the 100 different days and thinking of that as a vector. What is V2? V2 is, let's say, the air pressure, right? So it's just looking at the air pressure of 100 different days and then putting them together and so on, right? So that is, so it is, these are feature vectors essentially. So so now what we had is the actual labels y1 through ym, right? So this is the target labels, and what we wanted to predict was this W transpose x1, W transpose x2 till W transpose xm, right? So now, of course, we said that the way we were measuring it was y minus x transpose y squared. So that was our that was what we were trying to minimize, right? So one geometric way to see this is as follows. So now look at the subspace spanned by the vectors v1 through vd, right? Think of this gray area as a space spanned by the vectors v1 through vd, right? So each vector, if you see, is a vector which collects a particular feature, right? So v1 is one feature, v2 is one feature, and so on. So these are all m-dimensional vectors, right? So this is a subspace of an m-dimensional space. Let's look at that space, right? So what is our answer vector? Our answer vector, even before that, what is our target vector? Our target vector is y, which is y1 through ym. These are the actual label values, right? So that is also an m-dimensional vector. So that is this point in m-dimensional space. So these are our feature vectors. This is our target vector, right? So now we know that the way we are calculating the predictions is by linearly combining the features, right? So, and we want to find the best way to linearly combine features, right? So which means however linearly you combine features from your linear algebra class, you should know that your actual answer is not going to escape this space, right? So it's going to fall only in the gray area. Now all you want to care about is find that point in the gray area which is the best with respect to the y, which may not really be in your gray area. So the gray area corresponds to all possible linear ways of combining your features to get answers, right? So maybe this will correspond to some h1, right? So this point. So this, if you used a particular h1, which means if you had used a particular w, which is equivalent, then you would have ended up predicting in this point, right? So this is an m-dimensional point, which means you are predicting for all the m examples. If you used a different h, you might have ended predicting here, right? So now you want to see every point corresponds to a w. You can think of it like that. Now you want to find out that point which is best for you. In what sense? In what sense? It has to be closest to the actual labels, which is y, right? So which means what is the natural thing to do? Your y, if it's, let's say your y itself was here, what does that mean? Instead of here, if this was my y, what does that tell me about the data set? What is the error? It's on the same plane. The error is 0, which means what? What is our set of functions that we have considered? We have considered only linear functions, right? And for the linear functions, if the error is 0, which means the data is exactly following a linear model. That's what it means, right? So, but this may not always happen, right? So so as we saw, the data might have noise and so on. So which means that you not necessarily always will have a y that falls in this subspace. You may have a y that is outside of this subspace, which could be here. But then if you had tried to fit a non-linear model, then some complicated way you would have arrived at this point for which the error was 0. But we are not doing that. We are saying we will stick to linear models, which means what is the best linear model that you can find, right? So which means you want to find that point in this space in which you are allowed to search, which is closest to y, which means the error is as small as possible, right? So and that is this point, right? So, and what is this value? This is the squared error. Perfect. So this is our objective value actually, right? This is our error, and we want to minimize this as much as possible. So one geometric way of looking at least squares is you look at that, you take the target label, right, and then project it onto the subspace spanned by your feature vectors, right? And that is that will be your prediction. So this is one geometric representation of whatever we saw earlier. So it is the best orthogonal projection of label vectors onto the subspace spanned by the rows of X. That is our answer. So here is a question. So when I say orthogonal vector, it means so the vector y minus x transpose w, right? So what can you say about that vector's relation with respect to this subspace? It is orthogonal to this subspace. So which vectors in this subspace is it orthogonal to? Is it orthogonal to v1 or v2 or this x transpose w? So it is like, so let's say this floor was the place where we can actually search for, right? And I had a point here which is the target label, right? I'm saying I'm trying to look for the closest point here, right? So now my error vector is this vector. So is it perpendicular to just V1, just V2, or X transpose W, or everything? It's perpendicular to everything, right? So your Y minus X transpose W is actually perpendicular to every so V1, VD, right? So it is subspace spanned by each of these. Is that clear? So it is exactly in the orthogonal to this subspace, which means it is perpendicular to all of these. Now here is something that you can go back and think. So if I had tried to find a point which was not perpendicular to this, think about why that cannot be the minimizer of this problem, right? So if I had tried to find out a point which is not perpendicular to all these vectors, can that be a minimizer? If not, why? So that is for something for you to think about. Maybe we can discuss that tomorrow.